So I made this LinkedIn post related to the fact that eFabless has shut down and that I've started porting my libraries and starting looking into IHP PDK. And there was a suggestion that I make a video on how do I actually generate my standard set libraries, how do I generate my ADC, and how do I actually do the porting. So I can't make the video on how I ported the first library, because that's already done, but I can make a video about the second. But I think I should warn you, this video is very specialized and may be extremely boring. Because in general, engineering is not magic. It's not this fantastic inventive step. It's a series of very simple, targeted steps towards a goal. So let's try. Okay, so you should see my screen now. And that terminal is going to be way too small. We need to make it a lot bigger. Something like that. And we go into Pro ASX. If you have no idea what ASX is, then you should find it on my GitHub repo. I think there are some videos on it too. Okay, but anyway, ASX IP, that's where I have my different IPs. Maybe let's quickly have a look at the different ones. And let's, in addition to the terminal, open a text editor. So we have somewhere to edit files. And also here, let's make the font a lot bigger. Maybe 24, see how big that, oh, that's maybe too big, but let's try it. Maybe too big. Was it too big? Maybe it looks okay. Okay, so this ASX folder, that has a bunch of directories. And for, let's see, it's 3 years now, I think. Yeah, that sounds about right. Or maybe 4. 4 years since I started porting designs from other, like my ADC that was originally in 28 nanometer FD-SOI to Sky 130. I think I did that 3 or 4 years ago. I can't really remember exactly. Let's see if we can get the video centered. There we go. Now, Sky 130 is not really a technology that's easy to use anymore, so I need to port it to IHP. And all these different libraries are, different designs that I've been playing with. I think there's a PLL here, there's ADC, this is the ADC I taped out on Tiny Tapeout 6. And there's a bunch of designs, all the GR stuff, that's from groups in my course, Advanced Integrated Circuits, where I forced the students to make a temperature sensor. But then there's also some tools in here. The tools we'll be using today is CIC Creator. This is something I started writing around 2014, I guess, 10 years ago, 11 years ago, to automatically generate a ADC. And that's the one we'll be using today. So, let me first demonstrate how this works. So if I go into my newly ported transistor library, let's have a look at what's inside. So okay, let me write the command. And we want top. Couldn't find PDK root. Yes, then I need to set up my environmental variables. Let's just see what's inside that. So this just sets up my PDK and my PDK root. Okay, and we need to start that. So inside this library, I have sort of the standard cells that I use. These are not made for place and route. So if you're doing automatic place and route from digital, this is not the library you want to use. The library is quite big transistors. It's made more for the stray logic that you need in your analog designs. So you have your tie high, tie low, you have a tap cell to connect to the bulks and VDD, well, connect the N well and P well. You have inverters in a couple of different strengths, you have buffers, you have NANDs, NORs, Schmitt triggers, a couple of flip-flops. There are resistors, sort of just standard layout resistors, a 50 picofarad capacitor, and I think there's also a TSPC flip-flop. So all of this library is, if we look at the schematics for, let's pick the NANDs, you can see that the schematics are not drawn by a human. I mean, it's wrong, right? The PMOSs are on the bottom and the NMOS is on top. That's because this whole library is made by the CIC creator and the transpiler afterwards. But before we run that, let's look at the layout. Top. No, I need the library first. Top, come on. Magic, yes. And that of course opens on the other screen. Okay, so this is sort of the top level layout. It's the image that I put on LinkedIn. Actually, Sylvain, I think, asked how big this is. Let's actually figure that out. So it's 163 times 41. And if I open the Sky version, TR it's about there to there. And let's get the other one. So actually, they're pretty close in size. Or are they? Did I have the same content? No, I have the CapEx4 in Sky. So maybe we should do there to about here instead. Actually, it's pretty similar. Pretty similar. Yeah, pretty similar transistor size. Okay, that's good to know. So, of course, you can see the layout here is quite different. Let's get them on the same page or same view. No, same screen, I guess. So the top one is the IHP version, the bottom one is the Sky version. And we can see that these standard cells, if we take that one, for example, no, that was the IHP, 10 by 18. Eight by 17. Okay, so yeah, so roughly the same in both technologies. But you can see that both these are DRC clean. But I do not draw this layout by hand. I actually use the compiler I wrote many years ago to go from a description of the transistors and description of inverters, well, a description of standard cells and so on, into layout and schematic. And let me bring up the two directories. So inside these two libraries, there will be a directory called CIC. And you can see they contain roughly the same amount of files. There's a couple of more files in the Sky 130 version. And let's see. Let's take the digital JSON. And let's do actually, let's see. Thinking. So what I want to do now is I want to prove to you that most of these files are the same. So we can do SHA-SUM, I guess. So if I do ls1 xargs SHA-SUM, okay, that gives us the SHA-SUM for those, and then we can have a look. Okay, so the capacitor JSON, that's different. The SPI is different. Components, component JSON, that's actually exactly the same. The component SPI is different. The dig JSON is... Oh, is that different? Huh. That's different. Interesting. But the dig SPI is exactly the same. The DMOS, the transistor, that's different. And of course the technology file is different. And the IP is different. Okay, so actually quite a few of the files were different. But when we're talking about the differences, what do I mean? So let's do diff dig JSON, because that was different on the two, right? Yes. So there's no different in the SPICE file. What's the difference? Okay. Yeah, the only difference between the two files in IHP and in Sky is that I removed this no schematic variable, because then I actually generate the schematics again. Okay, so that's the only difference there. For capacitors, there will be more differences. But most of these files, and actually let's open up the digital so you understand. Most of the descriptions of how to lay out and create the digital components, and notice that the digital SPI, the SPICE file, that's exactly the same between the two technologies. And they're the same because they're technology independent. So for Ti-Hi, it has the same topology in any given technology. It has an NMOS, it has a PMOS, and there's a certain connection. You have a diode connected NMOS to ground, and that drives the gate of the PMOS and so on. So here we have the description of all the inverters and buffers and Schmidt triggers and switches and transmission gates with pull downs and so on. And in components, actually let's do the SPICE file. Component SPI, let's figure out the difference there. Yeah, so the only difference seems to be I removed the space and I removed the 4x capacitor. Okay, so there's very little difference in the SPICE description. So the circuit really. And as we saw, let's do it again here. For, let's see, was it a component? Yes, components JSON. That's actually exactly the same file between the two. And we saw for the dig JSON, that was pretty much similar. Now, what are these files though? So let me bring up components JSON. What this components is for example, in this case, this is the transmission gate. It is the instructions to the CIC creator, which is the compiler, on how should it be routed. Now, it's probably easiest to see for the inverter. So if I go into dig, let's take IVX1. Okay, so this is the recipe for an inverter. And notice that it was exactly the same file, well, pretty much, between the two technologies. Oh, where did it go? So when I did dig JSON, I said it was going to be boring. When I compared the two files, there were very few variables that were different. And there's no difference at all to the inverter. So it's exactly the same description in Sky 130 and IHP. And to illustrate how this works, let's go into Magic. And I think somewhere here should be the inverter. IVX1. Let's open that up. Cell down hierarchy. Okay. Okay, this is the inverter. The only thing that's, well, actually it consists of two cells. Let's just show that. So it has a PMOS and NMOS. And then there's a routing that happens for the Y and for the gate. And we can see the description here. So for the poly, it's routing from the NMOS gate to the PMOS gate. Now the name of this here is actually the instance name. So if I go into the dig spy and find the IVX1, it's these names here, MNMP. And then for the connections, it's really just routing from, well, for the YNet, it just routes from one end to the other end. Now, this may look excessive, but actually the way this JSON file works is that it's object-oriented. So when you describe the topology for how to route it up for the first cell, then you can inherit that for the 2x. So if I, I don't remember the command for go up. Oh, cool. Up hierarchy. So let's select the 2x cell. Is that down? Yeah, perfect. No, that's too boring. Let's select the, is there an 8x? Okay, perfect. Okay, so this is sort of the 8x inverter. And what you can notice is that it still just inherits the 2x. And the 2x inherits the 1x. So that inherits this description of the route. So I've only defined it once, but then it knows, okay, start on top left, that's the on top L command here. So that started this rectangle, go out, and then route in a down, bottom, over pattern for all the Y's. So it finds, it knows the Y's because that's in the spice files, right? So X1, X8. Here it can find all the rectangles on the Y's and then route those. And the same for the A's. And it says, okay, for the NMOS side and for the PMOS side, route vertically. Now, you could say this sounds incredibly cumbersome to write these instructions. And it is. It takes forever. It's extremely few people I know that have been able to use this tool. And that's kind of why also I'm hesitant of recommending this way of doing it to students because it simply takes so long time to learn. But for me, it's been a great speed up. And the reason for that is once I've done it, once I've described this is how an inverter looks, I never have to do it again. And all I have to do is describe the differences between the two technologies. So inside here now, I have a IHP technology file, and let me open up the Sky technology file. Okay. And I start at the top. So in my descriptions in these JSON files, there would be descriptions of the different layers. These are not the layers in the specific technology. So it's kind of independent. It's well, M1, M2, and M3, and so on. But then for each of these description, it has a concept for what in the SKY 130 does that correspond to. So for example, for metal 1, all you have to write in is a local I, and for this case, the other one is metal 1. And then it knows that, okay, when I go from metal 1, it has instructions from how to go up to metal 2. So next via, for example, and this allows it to create connections. Now, it also contains a set of rules and technology descriptions. So for example, inside here, I will have a unit, a grid size, and you will have a description of the technology and the technology files and how to find the symbols and the port order of those symbols and how they should be hooked up, what the parameters or names are, and so on. Here's a bit of a mix and match because some of the technology adaptation to IHP and SKY is unfortunately in the transpiler called CIC Pi, which takes the output from CIC Creator and then transpiles it into XGame and Magic. So that's maybe not ideal, but that's how it is. And then we have the symbol libs. I have made some transistors I like so that my schematics look the same independent of technology. And let's see. Then we have the IHP library. Okay, and now we get to the really important part. So for the transistors, as we'll soon see, there is a ASCII art description of the transistor. And there's really only one parameter that describes how to translate the ASCII art into a real thing. And that is these two parameters here, horizontal grid and vertical grid. So you can see that those are different between the two technologies. Many of the rules, these are the design rules, they're the same. But things like contacts are obviously different because that's very technology specific, and things like metal routing is very specific, and it has, for example, things like the fact that in most technologies you can have a via enclosure that needs to be longer on one side than on the other side, and things like that. And in the porting between technologies, quite a lot of the time is spent sort of in the rule or in this rule file to try and adapt to the same technology. And also a lot of time is spent on the transistor. So if I open up this DMOS file between the two, the first here, ignore that, there's details, but this is the ASCII art I talked about. And as you can see, the ASCII art is different. So I've had to modify and change how the transistor is generated for SKY 130 on the left side. That, by the way, took forever. It took some time to adapt to the style of Magic that has sort of different p-taps and contacts for the poly and N transistor and so on. So that took some time to adapt to. And then the one on the right side is the IHP. This took less than a day to get DRC LVS clean. Now, the coding of this, you can read the documentation for CIC Creator. I'm not going to do that. Very hard description now, but it's basically where you see an X, just fill the rectangle. Where you see this Y, what actually happens then is it looks for a pattern description. So it goes up and here and it says, okay, for a Y, I should go dunk, 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 and then leave a space. The hyphens are spaces or empty. So you can see that based on this for the poly, for example, it's going to be quite similar to how the transistor looks. Let's go to the IHP and let's look at the inverter, and let's look at the single transistor Was it the PMOS or NMOS we had back there? This is the PMOS. Select that and go into it. Okay, so this you can see is the description. So you can see that the OD, that's sort of, let's bring it up in the same view actually, so it's a bit easier to see the difference. Okay, here. Okay, so you can see the OD, that's this, actually, OD doesn't exist, but it's called PDIF in Magic. I just need the OD because my compiler expects there is always OD. It's actually not used, but you can see that's the same pattern. That will generate this pattern here. So for example, let me say I do that, and I have to go to the, let's close the terminal with the sky. Just leave the IHP one. Make IP, that runs all the commands. And let's close this. What's this? Yeah, that's the sky one. Sorry, I don't know how to make the magic window larger. But let me just flush everything here. Okay, that takes forever. We should open up just the transistor. But you can already see it's gone, that layer. And we can do it again. Regenerate the whole, now it regenerates the whole library, by the way. And we can, so flush, Lilo, TR, NCRDL. They work? No, I'm looking at PCH. Okay, so now you can see it modified the transistor. So that's really how this ASCII Art2 transistor works. So it's a bit of a pain though, because of course, in order to make it DRC clean, you have to sit there and modify. And modifying this ASCII art is actually as cumbersome as you would imagine. You sit there and you remove a couple of rectangles and you generate again and you figure out, is it clean? So that takes a while. But once it's done, it's done. You don't need to touch it. So that's pretty much all I had to do. I, of course, had to install the DK and so on. But I didn't have to describe the inverters in the library again. So if I can demonstrate here, let's go in the design folder. And this is where all the files are. Let's do ls lilo. So this is the library. And here we have all the magic files, schematic files, symbols, everything. And let's just delete the whole thing. Okay, so now it's gone. And let's delete that file too. Okay, there's nothing in design now, which means that if I take a reload here, I don't know if it crashes, but okay, let's demonstrate that it's gone. Try to open it, it's not there, okay? And the same for magic, if we want to prove that. Well, you can't do. Let's say it's obviously not there. So, but let's just see that. Yes, it's an empty thing. It doesn't exist. Okay. So now I usually wrap stuff in makefiles because then I don't have to remember commands. But when I say make IP, it actually runs this compiler. But let's do it by hand. First of all, it runs the. Does I have IP? That's CIC IP. No, it doesn't have one. Okay, so it won't run the first command. But let's go into design. And let's copy the command that is here. So what it'll do, it'll run this CIC program, CIC creator, and it'll give it a library location, which is the folder I'm in right, actually not in, yeah, So that's the CIC folder I showed you earlier. That's where it's looking for JSON files. And it will give it the one JSON file, the IP JSON. And it gives it the technologies file, and it says, okay, generate the library, call this. And let's look at that IP file. So this describes which files to include. So that's the MOSFET. Oh, I still call it Sky130. Ah, I should fix that. Let's do that now. DMOS Sky130. Let's just call it, rename it to DMOS core. Yeah, core is fine. Okay. Where was I? Yes. And the resistors and so on. Now, notice that it doesn't specify the SPICE files. This compiler, CIC, that will automatically find the SPICE files, because what it expects is a JSON file to describe how to do the routing and a few other things. And it expects a SPICE file to describe the connectivity and the actual sort of components. It also does the placement from the order in the SPICE file. I've written a paper on this. You can go and have a look at that. So let's run it. And now it's done. So now it's actually, it hasn't generated anything yet. All it has done is generate this CLC file. So you can see there's no magic files, there's nothing. So all there is this CIC. Now let's open that up. So that CIC file is pretty big. Actually, let's see how many lines. So it's 54,000 lines, and it's a JSON file. So if you go inside here, you will find, and let's do DF. Yeah, so this is the description of the flip-flop. So, for example, it has the cell name, and then it says, okay, it has a number of children, which includes ports at these locations, and probably also some text, some ports, and it has a few instances, and then it describes which instances and where should they be placed, and so on. And it has sort of a exact description of where to place transistors, inverters, everything in this, and all the rectangles in this flip-flop. And it's pretty long, as I said, 54,000 lines. So after that is generated, I need to go back to work because I don't remember the command. Then I have a transpiler. The transpiler, that's written in Python. So all that does is take this CIC file and load it into memory, take the technology file, load that in, and give it the library, and then generate the XChem, magic, and actually I'm not sure I use this last command anymore. And don't exclude anything. So that will have the knowledge of how to go from a pure sort of description of rectangles, XY width and length, or actually it's not XY width and length, it's X1, X2, Y1, Y2 of rectangles and so on, go to the magic format. And CIC Pi, CIC Creator, you can find them on my GitHub page. So there it's written all the magic files, and it will have written all the schematics. So if we now see in this directory, it will have all the magic files, all the schematics and so on, and the symbols. Okay, so if we now go back to work and we open the schematic. No, wasn't this the terminal where I opened the schematic? Let's see. Xchem. Yeah, it was. Okay, so now it's back. So, not automatic, but once the job's done, then it's easy to reproduce in a different technology. And so far, I've been lucky to be able to port it to most technologies. So, what I'm going to do now is I have a transistor library that I like to use for my designs because I'm a bit lazy. I don't want sort of a very complex. Let's just remove everything here. Okay. I have to create that. Now let's look at the old one. Okay, so in this library, there are a bunch of transistors. They are named after the number of contacts roughly and the gate length. It has two gate lengths, 1.2 times the minimum and roughly 5 times the minimum. So if we look in how they look, so we can do XCAM first. And then HC1F2, for example. And that's because I'm in the wrong technology. Okay, so here we can see it has 5.76 micrometers and 0.22. If we do the same thing with Magic and have a look at it there, and actually, let me open something different because I think I have top. Yeah. So in this library, there will be a PMOS that is 8C. There will be an PMOS that is 8C1F2. So two different gate lengths. And then NMOS and PMOS for both. And there will also be a magic file in this library. And my thinking behind this library is I want to make the layout as easy as possible to do. And also possible to do automatic. So this is the two transistor types. You have the PMOS and NMOS. Do I actually have PMOS and NMOS in the same thing? That shouldn't work. This shouldn't be DRC clean. Okay, that's a different problem. Oh no, they're all PCH. Okay, that makes sense. Yeah, they're all PMOSs. Anyway. Yeah. So anyway, you can see that they have the same size. Although they're different gate length, they have the same size. And that's just to enable, let's say, automatic routing, which I haven't really completed yet. But anyway, the sort of standard size transistors. Okay, so this is now the library I want to port to IHP. And I haven't done anything on it yet. So the plan for the rest of this video, and let's see if I have enough time because I have to go somewhere in not that many hours. But let's see. So I have no idea how long this is going to take. I don't know. I haven't done it before. So you'll see the real effort. First of all, let's create the library. So I want it to be called ATR, new IP. Really? Oh yeah, of course. Okay, file exists. Yeah. And we need to source the right PDK setting. Okay. Okay, so now we have a library, or not a library. We have a design. I want to make the CIC there, and I want to copy the CIC files from the Janeway version. Like that. And then I want to copy the TR, I want to copy the IHP technology file. So actually I choose to have a duplicate of these technology files because sometimes I have to modify the technology file per library, or per, not per library, but per compiled stuff. Let's see, we need to, first of all, let's look at the IP. Okay, so now the only thing I've done is copy that, get the technology file in, let's change the prefix. By the way, if you're wondering about these prefixes that I use in ASEX, there is a... Is there a... Let's see... No, git... Oh... Ah, there we go. There is a names file that describes the different project names. So I'm a big fan of science fiction, and especially women in science fiction for some reason. So all these different projects of the courses, which have been running since 2022, have been named after characters in sci-fi things. So that's why it's called the Lilu from Fifth Element. Anyway. Oh, and the reason I do have different names for everything is I want every single schematic to be unique, to have a unique name. And that's just because, yeah, I know that, what was I going to say? Yeah, if you're going to have a big chip, you can't have two schematics called the same thing, or two cells called the same thing. Then you will run into trouble. So better make a strategy to have them unique. Okay. Actually, I have no idea whether I've done enough now. We copy the technology file, so let's just run it and see what we get. Okay, that failed. Okay. Do I have the right PDK? No. Just need to load the PDK variables. Run again. Okay, perfect. Okay, so now it's generated all the layouts. Let's have a look. I don't care about the schematics right now because those I'm pretty sure is going to be correct. And let's look at one of the cells. Let's just look at the smallest one. Lilo, ATR, and let's do the NMOS first. And we want the 2C top magic. Yeah, we have 112 DRC errors. Not unexpected. Okay, so the layout looks the same, but we see we have some DRC errors. And let's just try and figure out what they are before we start trying to fix them. Okay, so DRC report. Okay, end diffusion overlap of end diffusion contact. Actually, just let's open up a single transistor. It'll make it simpler. I want the smallest one first, that one. Okay, let's see. Okay. Told you it was going to be boring. Seriously, the rest of the video is going to be me trying to figure this out. Anvil, overlap, or untap. That's that one. Did I have to do that manually? Wait. Okay, so this is the PCH. Let's look at the NCH first, actually. Usually the NMOS is easier to get DRC clean. So let's fix the problem on that one first. Okay. Poly spacing to diffusion. Okay, so that's that one. Fine. And diffusion overlap of end diffusion contacts. Yeah. We have via with... Right, okay. So we have to modify the transistor. So let's figure out transistors. Was that the one? We want the bulk P, bulk N. Now, these are the transistors. And let's actually open up the DMOS to see what I did there. Okay, so I ended up using 4. Okay, so let's do that here too. And I also see that ended up using that one and that one. Okay, so let's copy that strategy. Oh, they're not there, but and now I see I'm fixing the PMOS. I actually want to fix the NMOS. Actually, so let's go to that bulk NMOS. It should be down here somewhere. Yep, okay. Here comes the really boring part. The thing that's going to take forever. And I usually do alone without people watching. Like so many other things. Sometimes it's fun when people watch. So the pipette and NPAP, they look the same. Now here I'm uncertain though whether we need actually to have a bit more spacing. I think I ended up with more spacing for these transistors. Did I? Oh, actually 3. Really? Okay. I guess I have to do that then. It's going to take forever to get right. Okay, and now I have to count 1, 2, 3, 4, 5. Actually, fuck this. Let's see if it's actually possible to just get this right by changing the rule file. So I noticed I had 30 and 40 for the Sky one, didn't I? What do I have here? Janeway ATR. Really? 16 and 20. Did I have that for the TRL too? No, they're at 30 and 40. Let's see what happens. We want the flush Lilo, ATR, and NCH. 2C1F2. Okay, so now we're down to 4 DR series. Poly contact. Okay, so that's this part. Let's see if we can fix that quite easily. That's the DMOS. We want the... nope. Let's see, we were looking at transistors, right? And we were looking at bulk N. So let's see. The problem is that this... which one is it? So the poly overlap of this contact is too small. But which direction? Probably in the X direction. Yeah, that's 250. Okay, so we need a slightly wider grid, maybe. Let's do 32. 32? That's 234. Generate again. See if that's enough. Oh, that doesn't look good. It's off grid. Or it might be the grid in Magic, actually. Let's see. That sometimes is... yeah, it might be off grid. Doesn't look right. Let's try 32. Still 4 errors. Okay, let's do 40 then. It's maybe too much, but... still? Really? Okay. Well, the answer is 42, I guess. Yeah, that looks right. Okay, now it's DRC clean. But how big is it? Maybe that's okay. So let's see how wide it is. It's 1.2 times 0.23. How large is the gate? That's 40. So 1.2 microns. That's maybe not a bad size, actually. Okay, so maybe that's okay. Let's remove the grid off. Now let's have a look at the PMOS. Now the NMOS is clean. Let's look at the PMOS. I assume we'll still have the problem with the N-well, I think. But we might have some other problems too. I guess we need to flush everything first. Tech, magic, flush all. Okay. Let's see what we get. Now we have 10 DRCers. Okay. Yeah, now we have only the overlap of the end tap. Okay, so that needs to be fixed. So, where did I do that? Here, self. Okay, so that didn't work. Crap. Now we have to make it bigger. So I have this nifty function inside to just write, okay, add it. Well, maybe we don't have to do that. Does it use enclosures? I know my talking, yes, maybe. My talking is a bit sort of, what's it called? Staggered? No. Non-coherent. That happens when I think while speaking. That's horrible. Yeah, so it actually does. Okay, so now it should be DRC clean. However, is that going to work? Yeah, it should actually. Okay. Hey, it's DRC clean. Now we can look at the top. So let's look at the top. 2C top. Okay, here there is still some error. Poly spacing into diffusion. What is that from? Okay, so that's for this 5F. So let's load the 5F. Yeah, that doesn't look right. Okay. So what's wrong with that one? That may be a rule thing, actually. So let's look at the bulk. That's the top. Bulk P, that's the small one. Bulk P2, that's the big one. Min poly length 47. Okay. Let's look at what I did there in the sky file. with 11. Okay, so I think that's the Y. POB space, let's leave that. Okay, good. Now we have that one. But this one looks wrong. Let's increase that. Actually, is it clean? Yep, good. We need to fix the width. How much more? double. Ah, looks good. Still DRC clean. How wide is it? 1 micron. Perfect. I kind of like that. 1.2 by 1. Yeah, that looks good. And let's check the NMOS. And let's fix that too. Yep, and that's good. Okay, I think I'm happy with that. So let's open up the top. And now, yeah, the top's also clean. Good. And let's just check the other ones. So we have the 12C top. Clean. Actually, let's do it. Did I make it here? Oh, that's Lido ATR. Do I have everything in Lido ATR? No, I don't, right? I don't even have that. Right? Okay, let's do DRC, cell, Lido ATR, PCH, 12C, top, okay, 8C top, 4C top, good, 2C top, and let's check the LVS also. Ah, actually let's set the transistors, 1F2. Okay, so the transistor is correct. Okay, so that's correct. Yeah. Yes. Yes. Did I have some way of checking all of them? Ah, no, that's not there, right? Okay, maybe I did. Okay, so if I open up that one, and I open up the Janeway, because I in my mind I would have made some way to check everything, and yes, I did. Okay. Yes, there we go. Okay, but then maybe the LVSO that won't function. No, because why doesn't that function? Okay. Anyway. Now I'm curious. Why does this fail? Is it because it doesn't have any pins? Probably. Does that mean it doesn't write the netlist? Yeah, that might be a limitation. So let's see, it does write the top. Yeah, that's fine. Which one? PCH 2C top. Ah, okay, fair enough, fair enough. So Magic apparently doesn't write the netlist if you don't have any pins. Who knew? Okay, doesn't really matter. The library is complete. I have all my transistors now. It is DRC, and at least the transistors are LVS clean. So actually, let's put it out there to the world. I have to think. IHP, what did I call it? 13G2? Was that what I called it? IHP 13G2, yeah. Notice that as of yet, I have not simulated anything. And that would be the next step. However, I haven't been able to run simulations in IHP yet. And the reason for that is, let me just write this in. Let me commit this first. Do I need all this? Yeah. Okay, good. What was I going to say? Yes, why haven't I run simulations? Well, turns out I'm running on a Mac. And I need this open Verilog compiler in order to compile the models. And yes, I can run the simulation in Docker, but that's going to be slow long term, I think. So I just haven't set it up yet. But it's transistors. You don't really... Well, I do need to simulate them to get the GMIDs and things like that out from them. Let me show you how I have it for the old library. Is that in here? Or is that then? No, actually, yeah, we have the Connor version. That's okay. So this is one of the old transistor libraries, and I do simulate everything. So I get for a GMID of 10, I know what current to put through, and for 15 and so on. So that's simulations I need to set up and run. But already the layouts there, it's possible to do that anywhere else. So that was what I intended to show today. A relatively, I reckon, a relatively boring video. But there was a demand for showing how I ported things. And actually, maybe we should do one more thing. Let's see if we can port our SAR. Not our SAR, my SAR. New IP. I'd be surprised if that's... let's see, SAR 9-bit. Yep. If that's DRC clean. Do the same thing. Make their CRC. CRC. CP. Sun. SAR 9B. Actually, we want... Which... I just want to have to make sure... I want to make sure that I have the right version here. Yeah, it's the main branch. I think that's okay. Okay, so that has the DMOS core. Let's remove that. And remove the sky. And copy in. Let's use the one from the TR library, because that has the DMOS. And we need the IHP technology file, and we need the DMOS that we made. And I need to go into that IP file and modify the link to the DMOS. DMOS core, I guess I called it. Like that. And let's generate the ADC. Ah, first snag. Yeah, that I don't think I can fix today. Can I? Okay, so the ADC uses parasitic capacitors. Yeah, parasitic capacitors. So just like moment capacitors where you have the parasitics between metal lines. In order to get that right in the schematic, then it needs metal resistors. And I don't think there were any in the IHP library. So I don't think this is going to work. Maybe I could modify it some. Let's have a look at the... No, that's not it. Let's do... It's probably in the RM1. Oh, I still got SAR. We should fix that too. We want... Okay. So I think the one that's going to fail is this one. Yeah. Because it doesn't know how to create a metal resistor. So let's see if there's now anything in here that looks like a metal resistor. No. There's an RCL, there's an RPD. Yeah, there's nothing like a metal resistor. Should I just make one? Yeah, let's do that. I think that's going to work. Opt, PDK, share, PDK, IHP, and I don't know where it is. Let's say it's in XGAM. Let's take that symbol. Call it an RM. And let's... What's this DRC thing? I think maybe that's... It won't simulate, but that may be enough. So... Wait. How does this look? Just copy these. And let's call it not Sky, but SG13G2 and PR underscore, I think I called it RM, was it? Is that what I called it? Yeah. RM. Did have what was the pin list? Ports. MP. Okay, so that's MP. That's fine. Width, length, yes. No. LW. Microns. Oh, this is the... Yeah, let's leave that. The resistance will be wrong, but I think it could work anyway. Like that. Let's see if it runs now. Something else failed. Oh, okay. Yeah, I know what it is. I have all this don't generate schematic things because when I clean out the schematic, then I don't want to override it. Okay, then just fix that. But that we can just fix like that, and hopefully it'll run again. Okay. Interesting. Okay, so now it's generated my SAR. And I guess it went to SAR 9B. What do you know? Wow, really? No, that can't be true. Wow, cool. So that's the SAR, and there are 9. 9 DRCers. I was expecting a lot more than that. What are they? That's actually pretty good. Metal width. Okay, metal width less than... Okay, now I got interested. Maybe we can actually get a DRC clean. Oh, wow. Okay, maybe not. Where's the problem? Ah, that's it. Now that may not be too trivial to solve, actually. Or maybe I can cheat. So if I increase the vertical grid to 22, does that make the problem go away? Now, of course, what I just did will change my transistor sizes and actually modify the whole layout. So look closely at the screen now that I flush everything, and you'll see absolutely everything changing. You see that? So it redoes the whole layout. And we're actually down to 1 DRC here. Okay, what is it now? Metal width. Oh, that's weird. Ah, right. This is this will be actually this will be an actual error. Ooh. Now that's not easily fixable. Is it? So how would I fix that one? I may have to change the order of the routing. So that's that one. I don't want to push it. So how did I decide the order of the routing here? This is something I did many, many years ago. That's probably determined by the route rings on this thing. So if I change the order of the cap, what do I call that? CDAC? Oh, so that's compiled. Yeah, this may be something that takes me a bit more than a few minutes. And I really should jump in the shower soon. So which signal is this? This is one of those random events. I have no idea which signal this is. Oh yes, I do. D4. Okay. Yeah, but it just does all of them. Okay, let's cheat a bit. Cheating is good, so if it worked with 100, let's just change that to 22 and see if that fixes the problem. No, that just gave me a bunch more DRC errors. It did fix the problem though, but I got a bunch more. Okay, but that problem I think is maybe more fixable, because that's related to the track length or the routing. That's not going to be there. It's going to be here, right? Yes. So it's not going to be that one. Not that one. Is it those? No. 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 well, how do I control that? It's gonna be in... Here we go, I think. So this is the DigX. Okay, so that's definitely the DigX, and it should be these port files. Or was it? Here we go. That's the one. Oh, whoops. I think. Those are going to move, those wires. Yes, they did. Still a problem though. Okay, so there's still a problem with the run length. So let's go 1, 2, 4. Okay, that's not going to work. Yeah, there's a problem on that side. Let's just sign 8.5, 2.5, 4.5. Okay, down to 36. And actually, that's the... Oh, I really should go. But this is so fun. Okay, so now that's not a problem though, is it? Yes it is. Because I can't move that further. Can I move it down? Wait, what? There we go, add port here. So start layer, stop layer, port, path, V cuts, H cuts, X offset, Y offset. Okay, so let's do that -1 then. Was that for the second one? Yeah, so 0.5 -1. Now you should realize that almost everybody else than me would have a close to impossible time figuring this out. Okay, did it move it? Did I move the CP1? Yeah, I did. I wanted to move this. Was it which one? CP0. And you may say, this looks like a lot of work. Can this really be faster than manual? And, well, I haven't gotten to the end yet. Metal spacing, still a problem. Okay. Yeah, but that's... Wait. If I do a CP1... Okay, then I have to get into that problem, because there's some metal 3 there. Bugger. Okay. Okay, so that can't be... Let's do source 0.6. What is the distance here? .22, so I don't think I have that much margin. I may actually have to increase the... Can I regenerate it? I may actually have to increase the horizontal grid even more. Yeah, because now I get a problem on the other side. Okay. So the thing about what I'm doing now is I'm really adapting the topology of the SAR layout to the specific technology. And it's really hard to predict how all of these problems are going to occur, right? Because when I made this ADC, I made it in a totally different technology with totally different metal spacing. And it's almost impossible to predict how it's going to work in this specific technology. So what I'm doing now is just trying to find solutions that actually gives me a DRC clean layout. And hopefully that is possible. But I don't know whether it's possible or not. It may not be possible. Okay, so is it still spacing errors? So now that's just that one. But I think I have some margin there, so maybe I should just try 1, 3, 5. See if that's sufficient. Okay, 4 DRCers. Ah. Crap. Now I made the grid too big. Let's do 26. 2. Okay, getting there. Okay, what's this one then? Metal spacing, M3. What? What's the problem? Ah, fucking hell. Sorry. Sorry for the swearing. Okay, so that's because the routing width is not the same as the width of. So that's 21, and that's 20. Okay, so let's just change the metal routing width to 21. See if that makes everybody happy. Crossing fingers. Come on, come on. I really need to go hit the shower. Yo, wow. Hey. Fun times. Now, C star. Okay. Look at that. The ADC is DRC clean. Now the interesting part is how big is it compared to the Sky one. So notice that what I had to do now is sort of increase the size a bit, move a couple of ports around, shift a bit where the structure is routed. But really, how long did that take? I don't know. Half an hour? I didn't pay attention to time. So it took me half an hour to port a complete 9-bit ADC into a different technology. I have a complete layout now. That's DRC clean. I'm pretty sure it's not LVS clean though, because I did, well, there could be shorts somewhere that I haven't found yet, and there could be, there's probably problems with the fact that we don't have the metal resistors in the IHP yet. But even a DRC clean ADC in about half an hour is a really good thing. And actually it's not one ADC, I believe. If I open the library manager, I don't remember, did I make an 8-bit version? So I know the ADC I taped out on Tiny Tape Out 6 was actually 8-bit. So that was a reduced version on the one you're looking at now. But yeah, it's here. Let's see if that's DRC clean. And it is. Cool. Wow. Wow. Excellent. So I made 2 ADCs in half an hour. Let's have a look at the size difference. That's always fun. Hey! Happy now. Very happy now. I didn't expect to get that working so soon. It's always a magical thing when I port the ADC to new technology. And you can see it's cumbersome, right? You have to know quite a bit what to change. But still, it's 10 years ago since... Yeah, it is 10 years ago since I first taped out that ADC and first wrote that JSON file. And I haven't modified that much. What am I doing? I'm opening that one. Magic. SAR 9B. Let's see if there's a size difference. Now, it could also be that by optimizing the layout a bit, optimizing the real file, I could actually get it smaller. But let's just see how it is now compared to the Sky version. That's not it. I want that library manager. We don't want the 9-bit. Load that. Okay. Now we need to find the right terminal. That I think are the transistors. What's this? That's the sky. Okay, this is the one. Hey! Wow! 108, 242. 142, 269. So it actually is smaller in IHP. Doesn't look like it though. So that's the... It should be possible to set the box. How do I do this? 150, 300. Does that work? No. I was thinking about getting the same size in the two windows, but anyway, that didn't work. Okay, but that one is 108, 242, and the one in sky is 142, 269. So it's slightly higher and slightly fatter, which should mean that the 8-bit version is actually smaller in IHP. And of course, yes, I need to simulate and so on. But it's a good first... That's the thing, this ADC was made to be extremely portable. The architecture and the way the whole bit cycling works is extremely robust against technology changes. Let's see if that's also the smaller. So 98, 174. Yeah, it is. Slightly smaller. Seems like the caps maybe take up a bit more of the... yeah, and the digital logic is a bit smaller. Cool. Okay. I think that's enough for today. So, yeah, I did not expect to port the ADCs that easily. That's cool. I still need to figure out that resistance problem though. So if any of you have some ideas on how that works, then please let me know. I need to make a picture now to post on LinkedIn on to say that I ported my ADCs to. Okay, see you later.